because the problem set 5 is a little ahead of where a little more, includes topics that I haven't gotten to and won't get to properly today. I've pushed its deadline even farther back. It's now officially due on Monday. And with that, probably I've eliminated one problem set from the class, which we'll deal with in an equitable way. And is almost always happens. It's been a long time since I managed to get all 10 problem sets into a semester. So problem set 5 is due on Monday. Some content things to look back on and as we head forward through balloons. First one that comes to mind is that the buoyant force appears in our atmosphere because of gravity. Why do you need the buoyant force when you got gravity? Well, any portion of air that's here that I can sort of identify with my hands, the fact that it's motionless and staying motionless, assuming no wind and all that, means that it's experiencing zero net force. It's at equilibrium, and yet we know it has a weight. So if it's got a weight and there's zero net force, something must be pushing up on it with a force equal to its weight. What's the something? The only thing that could possibly do this is the surrounding air. So the air has to develop a pressure gradient to push on air itself. To keep this blob of air that I'm pretending to hold my hands from moving, the surrounding air has to support its weight. And it does that by developing a pressure gradient. Highest pressure down low, lowest pressure up high. There's a smooth variation in pressure all the way up to the top of the atmosphere. And that pressure gradient not only supports the air itself against the pull of gravity, but it supports anything immersed in the air. So you guys are experiencing this upward push. Balloons experience it. It's called the buoyant force. And the strength of that buoyant force, as cleverly realized by Archimedes 2-ish thousand years ago, was it's equal to the weight of the air that would have been there if whatever's displacing the air hadn't displaced it. Questions about those observations? As an aside, potentially related to the problem set, anytime air needs to be pushed, the air in the middle of something needs to be pushed, how are you going to push on it? Well, gravity is unique in being able to reach into the middle of the air and pull on it. That's a special case, but otherwise, the only other thing that can push on the air is the air, and it pushes by way of pressure gradients. So if there's a situation in which the air needs a shove to make it do something, to make it accelerate, for example, it needs a pressure gradient. All right? The other thing I wanted to look back on and talk about is the idea of density. I told you the density for fluids, we have sort of new physical quantities to talk about because fluids have characteristics. And again, fluids are both gases and liquids and things that have no fixed shape. They have physical quantities that are more useful for them. Force is often not so useful because how much air are you talking about exerting a force? So we use pressure in place of force, and instead of talking about mass, we use mass per volume, which is density, to describe, to characterize a gas. Density is actually pretty useful in the following observation, that if you've got a blob of air again, let me give substance to the air. So, okay. Much easier balloon to blow up. Okay, I'll tie it off because I can. Okay. So if I take the balloon away, the air is still there, and it's being supported perfectly by the buoyant force that acts on it. So this balloon is experiencing an upward push that is equal in amount to the weight of that air that it's pushing out of the way. That's Archimedes' principle. Whether or not this balloon will float depends on its weight, its own weight, the total weight there, compared to the weight of the air that it displaced. If If it displaces more than its own weight in air, wow, great, it's pushed upward harder than gravity pulls it downward. It will go up, and we'll do two balloons like that, hot air and helium. If, on the other hand, it weighs more than the air it displaces, it's under-supported. It's pushed up by a buoyant force that's not strong enough to support its weight, and down it goes. And if by a miracle it's pushed up just right, it'll hover. If I let go of it, it'll just sit there motionless. You know from experience that air-filled balloons descend. Why? Because they have, the rubber weighs a lot, and the air inside is a little more dense than the air outside because it needs the pressure to hold the balloon. It needs extra pressure to hold the balloon stretched. So far, so good? Or questions? Another way to look at this situation in terms of density is, if the average density of the balloon, which is to say the mass per volume, even though it's not uniform, it's got chunks of rubber, it's got bits of air and so on. If you take its overall mass and divide it by its overall volume, you get a density, an average density. If the average density of the balloon is greater than the average density of the air, that's the same story again, thought of a little bit differently, but that balloon, if it's got too much density, it's under-supported, it's going to go down. On the other hand, if it's got less density on average than the air it displaces, less mass than the air it displaces, less mass per volume than the air it displaces, it goes up. So for things to float in air, float upward, they need to have an average density that's less than the air they displace. It's just another way of looking at this buoyant issue. Is it over-supported, under-supported? Questions? All right, I think feel like I filled in things that I left out. All right, to make a balloon able to be lifted upward by the buoyant force, as I just said, it either needs to, two ways of looking at the same thing. It has to weigh less than the air it displaces, or its average density has to be less than the average density of the air it displaces. Same ideas. How do you do that? How do you make a balloon that has that's so light? Well, you can't fill it with nothing because it'll get smashed by the surrounding air pressure. So you have to fill it with something that will provide the air pressure you need to keep the balloon taut and happy, but not have very much mass and therefore not very much weight. What you're going to do? Well, we already saw that you can change the properties of a gas by playing with it in various ways. If you pack the air molecules more tightly so their density goes up, their pressure also goes up. That was one relationship I already have brought forth about the connection between density and pressure. If you keep everything else the same, and everything else is typically the temperature, don't play with the temperature. Packing the molecules more tightly gives you more pressure, and it's pretty much proportional. Double the density of the air, which is to say you double the number of air particles per volume, you double the pressure. Simple as that. What else can you do? Well, you can change the pressure, or you can change the gas, I should say, just in general. If you start playing with temperature. We play with density, and you get more pressure. As density goes up, pressure goes up. What about if you change temperature? What if you increase temperature? If you increase temperature, keeping everything else the same, and everything else in this case is density. Don't add or subtract molecules, just heat it up. When you do that, the atoms and molecules move faster, they hit more often, they hit harder. And the result is each one contributes more to pressure than it did before. And amazingly enough, if you double the temperature of an ideal gas, of a typical gas, you come pretty close. If you double its temperature, you double its pressure, keeping everything else the same. In other words, don't change the number of molecules you got, or what kind of molecules they are. So increasing temperature increases pressure as well. As I said a little bit last time, and I was just trying to get in whatever I could get into the hour, the temperature, when you double it, you got to do that on what's called an absolute temperature scale. A scale which 0 is 0. The 0, absolute 0. It turns out that when you do that, when you double the temperature, room temperature is in the most widely used, in fact, the metric official, it's not even metric, in the SI system of units, the ones that scientists use, the measure of temperature is the Kelvin scale. And room temperature here is just under 300 Kelvin. It's like 293. So about 300 Kelvin. So if you go from 300 Kelvin to 600 Kelvin, and 600 Kelvin is the high end of a stove, of an oven, about 450 Fahrenheit, something like that. If you double the temperature, you double the pressure. So if you take a can of air and put it in the oven, turn up the heat, get it up to the high end of your oven's temperature range, the pressure inside, instead of being 1 atmosphere in pressure, it'll be about 2 atmospheres of pressure, twice atmospheric pressure. And that's just because the molecules are hitting harder and more often. Thoughts, questions? Okay. So if you take a balloon full of air like this, and if we were to heat the balloon up, and not the surrounding air, if we were to heat the balloon up to twice its current temperature on an absolute scale, the air particles in there, they're trapped, of course. They would push outward twice as hard. The balloon initially would have a terrible pressure gradient across it, pushing outward. The balloon would swell, and as it swelled, assuming it didn't pop, the density of the particles inside would decrease, right? Because they're occupying more space. And what will happen is the balloon will swell until the pressure inside is pretty close to the pressure outside. That's the only arrangement that a balloon can tolerate for any length of time. It needs pretty much the pressure's a little higher, but we're talking a smidge higher inside than outside. So the balloon will swell as it heats up. It can't sustain huge pressure inside, low pressure outside. It'll puff. And where it'll settle down is with the air inside pretty much at atmospheric pressure again. It'll be hot, but the density will be very low. How's that? Well, the density is low because the air particles are more effective, each one, at creating pressure. So you don't need as many in the same volume to create atmospheric pressure. They spread out and they create atmospheric pressure in a bigger volume. So the balloon now is twice its original, it will go to about twice its original size. The temperature will double, but the density will halve. And when you look at twice the temperature, half the density, you come back to atmospheric pressure again. Pretty close. Can you follow that idea? If you fill a balloon with a rubber balloon like this with hot air, it will swell. And it will be still pretty close to atmospheric pressure, but it'll have about half the density if you get that hot. Well, instead of taking a balloon like this and puffing it up with hot air, we're going to take just a bag and fill it with hot air. The air that will go inside will have to be very close to atmospheric pressure. If it didn't, the air will accelerate from high pressure to low pressure, and it'll move. So for things to be stable, the pressure inside the balloon is going to have to be very close to atmospheric pressure. But because we're filling it with hot air, each air molecule does a better job of creating pressure. You don't need as many in every packed space. There will be fewer air molecules inside the balloon, the bag, than there would be if we filled it with room temperature air. Any questions about that idea? So the balloon will contain a gas at atmospheric pressure, so it won't smash, but it's going to be a gas with about significantly less dense than ordinary air. There are just not as many air molecules in every liter. All right. So I'll turn on the blower. It's like a hair dryer, but it's really hot hair dryer. You do not want this on your hair. Okay. So hot air is blowing in, cold air is being displaced out the bottom. So I'm not packing, I'm not just adding more air. There's actually air flowing out. Cooler air is flowing out, hotter air is going in. The hotter air has less density, fewer molecules, and the bag is now full of atmospheric pressure air, but with a very low density because it's so hot. Woo. As it cools off, it can't sustain the pressure with the same density. Air has to come in to replace the air to add molecules to build up the pressure again. So as I heat it, there's a net flow of air molecules out of the bag. It's got fewer air molecules now than before. It's lighter than it was before. Its density is lower than what it was before, and up it goes. And I think these bags, you can actually blow them up and seal them, and they can use sunlight to heat themselves up. So you can just send it off and cause all kinds of trouble. It floats around up in the air. Any questions about why that bag floats? Anything? You see, particularly during the fall and spring, around here in the morning and the evening when the winds are low, you'll see a lot of hot air balloons floating around. They operate the same way. They use a burner, typically a propane burner. They put hot gas up into the balloon, and because it's hot, it doesn't need very much density to create atmospheric pressure. It's very light, up it goes. They have to monitor how long they keep the balloon hot because it degrades the fabric, so that there's a lifetime, a heat lifetime of the balloon. They eventually have to discard it because it goes past its sort of regulated period of time. What else? The hot air balloons work best on cold days. Why? Because cold air is denser at atmospheric pressure. If it's cold, to create atmospheric pressure, you need to pack the air molecules more tightly together. So cold air is denser. It's got more mass per cubic meter, therefore more density, and displacing it gives you a stronger buoyant force. So those balloons float better in cold air than they do in hot air. You can go on forever with all these little details. Any questions about hot air ballooning? All right. So that's one way to make a lighter than air balloon is to use hot air. This is just the story of temperature. I told you that you need to, when you're looking at the effects of multiplying the temperature by factors, you have to do it in an absolute temperature scale, and the classic temperature scale is this Kelvin scale or Kelvin. It's actually, they're not even degrees, it's just kelvins. And room temperature is close to 300 of those, 300 Kelvin. I showed you liquid nitrogen the other day, and liquid nitrogen is like 78 Kelvin, so it's about a quarter of room temperature on an absolute scale. Okay. What about a helium balloon? Helium balloon does something different. I've showed you that if you increase the density of air, keeping everything else the same, the pressure goes up. I've showed that if you increase the temperature of air, keeping everything else the same, the pressure goes up. What if you change the air itself? If you substitute for air particles, you substitute helium particles. Do I have a picture like this? No, I don't have a picture like this. Doesn't matter. If you substitute helium particles, which are atoms, amazingly enough, a helium atom thrown into the middle of a bunch of air particles, it's a little teeny guy, tiny mass. The helium atom has about 1/7 the mass of a normal air molecule, of the most common air molecules. And yet, it contributes just as much to pressure as the air particle, as a typical air particle. Why is that? The little teeny helium atom traveling around with its dose of thermal energy. When you look at the statistics of its thermal energy, it turns out it gets the same amount of thermal energy on average as all of its bigger buddies. And in order to carry with it that thermal energy as kinetic energy, it has to travel faster. So helium atoms in a gas, there are some in this room right now. They're rare, but they're there. They're traveling faster than the other particles, considerably faster. They travel pretty close to 1 kilometer per second. So they're little, but they travel fast. And as a result of that added speed, they hit more often. Whenever they collide with surfaces more often. And when they collide, the fact that they're traveling so fast means that they compensate a little bit for their, well, significantly, for their low mass. They're still able to transfer a pretty good wallop of momentum. The long and short of it is that if you have a balloon full of air, so here I've got one, this is a balloon obviously full of air, right? And let me fill another one with helium, just because I can. I want them about the same size. Oh, this is leaking. Like, come on, stop leaking. Okay. I need my hand props. All right. So this guy's full of helium. This guy's full of air. They're pretty much the same size. They have about the same number of particles inside. They could both have about atmospheric pressure, about the same volume. So the gases in these two balloons are doing about the same job. They're both providing atmospheric pressure in about 2 liters maybe of space. The helium balloon has the same number of particles in it. That is the little, count the atoms, 1, 2, 3, 4, 5, 6, 7, 8, 9, a zillion. There are 1 zillion in here, and there are 1 zillion air molecules in here. That comes about because the size and mass of the particle in a gas doesn't matter. They count one, each one contributes the same amount to pressure. But the helium particles weigh so little. They have tiny mass, about 1/7 of the mass of the average air molecule. And so they have about 1/7 the weight of the average air molecule. So this balloon is filled with a gas that weighs about 1/7 the gas in this balloon. You okay with this? Or questions about this? Yes. Okay. Because the helium balloon has less mass than the air around it, it's going to get pushed up. That's exactly right. This balloon, as we know, has a little too much weight, partly because its gas is slightly more tightly packed than the surrounding, and partly because the balloon's skin, rubber itself, is quite dense. It's a sinker, right? No, I didn't mean to pull it down, right? It doesn't float. It's under-supported. This guy, because it has a gas inside that has, the number of particles is there. It's described by a new physical quantity that's it's called particle density. Both words are important there. Ordinary density is mass per volume. Particle density is particles per volume. These two have the same particles per volume. Because they're at the same temperature, same pressure, that's how you end up with, you get the same particles do the job. But because the particles are so dinky, they weigh so little, when I let go of this, it goes up. You okay with this idea too? The so-called lighter than air gases. They're simply built out of particles that are smaller, and certainly they're physically smaller in size, but they're also less mass and therefore less weight, and they can still create the pressure you need, and they hold off atmospheric pressure, keep the balloon inflated, but they weigh so little the balloon is able to be supported and over-supported by the buoyant force, and up it goes. All right? There is sort of mythology that if you keep going smaller with the weight of the gas, that you get more and more lifting ability. Like if you go to hydrogen versus helium. Hydrogen gas each particle has about half the mass and half the weight of helium. So hydrogen would be even better, it seems. Well, the difference is very small in terms of its ability to lift stuff, because the gas in there already weighs so little compared to the surrounding air that the gas is almost as though it had no weight. The difference between that gas, the air is pushing up on something that weighs 1/7 of its weight, and you get an upward lift. If it pushed on something that weighed 1/14 of its weight, the upward push would still be way bigger than the weight, and you get a slightly bigger ability to lift something along with the hydrogen. If you're lifting helium, up it goes. We could weight that down with paper clips and find the point where it just barely floats, and it would take, say, 7 paper clips or 6 paper clips to hold it down. If we put hydrogen in it and started weighting it down with paper clips to see what would make it float, well, the hydrogen weighs a little less than the helium, but we would probably only be able to carry 1 more paper clip before we made up for the difference between the weight of hydrogen, which is very little, and helium, which is just a little less than very little. I don't know whether this is making a lot of sense to you, but the point is shifting to hydrogen doesn't let you lift very much more. You can take that as just a factoid, if you like. Hydrogen has the bad feature that it burns. That didn't prevent me from making hydrogen balloons for my sister's birthday parties. Nobody, stay away from the flames. I couldn't make helium. You can't make helium. That would be the alchemist's dream. You can't make elements, but you can make chemicals, so I could make hydrogen. One of my roommates, before he was my graduate student roommate, we were in high school together, and he would fill dry cleaning bags full of various gases that were lighter than air and that burned. And I will show you actually one of them. He would fill dry cleaning bags full of gases, send them off with a fuse attached. They'd go up 1,000 feet, they'd burst into flames, and then he would listen to the police radio for all the UFO reports. Yeah. He never got picked up by the police. There's no justice in the world. So I want to show you one other familiar lighter than air gas. Propane is not lighter than gas. The propane molecules are pretty big. They're heavy. They go down. They don't float. Methane molecules, so-called natural gas, they're tiny little molecules. They weigh about half what a normal air molecule weighs. They're lighter than air. Incidentally, this difference between natural gas and propane affects appliances and stuff. This is why when you have a stove, a gas stove installed, you have to, when you choose between propane, which is heavier than air, and methane, which is lighter than air, you have to change some of the fittings. So public service announcement, this may happen sometime in your future. This demonstration requires somebody to light the bubbles on fire. Can I have a volunteer? Somebody who likes to burn things. Oh, come on. Nick. Thanks. You get to be the lighter. I'll be the bubble blower. Okay. Your job is to chase the bubbles, not too close to me. Wait for them to get up there, okay? Not bad, right? You don't get to do this in an English class. So we're, again, filling these bubbles with atmospheric pressure gas. It happens to be made of so the particle density in these is the same as, oops, oh, you're out. He's holding a thing spraying natural gas in one hand while he's lighting something in the other. I survived childhood. It was Many close calls. All right, you get the point? Yeah, thank you.
Is this safe?
I think we're all safe, yeah. You can just, yeah, thanks. Yeah. Another memorable moment from high school. I wasn't involved in this, but there was a chemistry demonstration that was videoed actually at the university where I lived. And they were doing what's known as the thermite reaction between aluminum and iron oxide. And it's burning away here beautifully. And sparks came out and hit the screen. And the screen burst into flames. And so the video is showing like the chemistry auditorium was flames shooting out of the projector screen. You know, do it again. All right. Anyway, so that's balloons floating. Let me just bring you to the ideal gas law. To put everything sort of in perspective, the physics portion of this program, coming back, is that there is a relationship. We've already seen that there are relationships between pressure and the density of the gas, the temperature of the gas, what the gas is. How do you deal with all this? The relationship that is conventionally described, and it's called the ideal gas law because it assumes the particles don't interact with each other. They don't stick, for example, and become liquids. As we saw, if we cool air too much, it violates the ideal gas law big time because it turns into a liquid. That's a no-no. But even the air particles in the air, as they are normally, they hit each other and they kind of go like, wow, you know, you're kind of attractive. I'll stick around a little bit, and they mess up the ideal gas law a little bit. So this assumes no chemistry, and it simply observes that the pressure is proportional to temperature on an absolute scale. We've seen that idea. You heat it up, the particles are going faster, they create more pressure, each one. And it's related to particle density. It turns out that what the gas is doesn't matter. I mean, again, assuming ideal. Whether it's air, whether it's helium, that doesn't matter. It's how many there are packed into each cubic, whatever, a liter. So that was the most important characteristic, was how many particles there are per liter. If you increase that, if you crank up the density by packing air molecules more tightly together, pressure goes up. Pack helium molecules more tightly together, pressure goes up. Substitute helium particles for air particles, no difference. Just the particle density matters. Then there's a constant of nature. It's just called Boltzmann's constant, after one of the physicists who was involved in developing all this theory. Okay? So that's the ideal gas law. And that's pretty much the story for balloons. Any questions about balloons and balloon? You know? All right. I'll call it a day on balloons. Now, it brings us to water distribution. So I've talked about one type of fluid, gases, at least in various contexts. Now look at another type of fluid that's important to everyday life, which is water. And how do you move water around? One of the most, let's see, some of the differences between waters and gases. Water has pressure as well. It definitely does not follow the ideal gas law because the water molecules stick to each other. They're completely not ideal. Its most important feature that differentiates it from gases is that water is essentially incompressible. You can't play with its density. The density is given to you by the liquid. When the water molecules all stick to each other, they pretty much pack in as tight and snug as they can get. You can't change that significantly. So you can't compress them more tightly together. You can't spread them out. Water's density has a relatively fixed value. It's not exactly fixed. There are things you can do to change it subtly. But for the most part, it's got a density of about 1 kilogram per liter. You've never gone into the store and bought water where the liter bottle had it's always a kilogram in that liter bottle. You never get a half a kilogram in a liter bottle or 2 kilograms in a liter bottle. It's 1 kilogram, give or take a smidge. All right? So water is incompressible. You try to squeeze the bottle of water, it doesn't get more tightly packed. You can pack gas molecules. You can increase their density, decrease their density. You can play with them all over the place, not with liquids. All right? I've now beaten that to death. All right, so water distribution, it's important to you because you open the tap in the bathroom and water, or the kitchen sink, water comes roaring out. How did it get there? And what are the issues governing it getting there? What can go wrong? You know that during a power failure, you may well lose water pressure along with everything else. If your pipes get old and rusty, you may find that they don't deliver water very well anymore. What's going wrong there? They have the water system in a house, the water system in a skyscraper, the water system in a town. They're complicated things. And sort of what are the issues involved? Okay, so I'll open this whole thing with one of my questions here. So water enters your house somewhere just below the surface of the ground. But basically it comes into your house at ground level. And if you've got bathrooms on all the floors, where are you going to get the strongest shower? That is the most stinging spray of water out of the shower. At the ground floor entry level, in the basement, or up in the second floor. Everybody okay with the question? Questions about the question? All right, how many think that you're going to get the strongest shower right there where the water comes into the house? A. How about in the basement shower? How about in the second floor shower? Oh, you guys are all geniuses. Yes, it's in the basement shower, and it's just a matter of energy. It's just a conservation of energy problem, as we'll see. If the higher the water is, the more of its energy is in the form of gravitational potential energy. So there's not much energy left to be kinetic energy for a stinging spray of shower. The lower you go, the less energy is tied up as gravitational, and the more is available for kinetic energy. So you get higher water pressure and consequently higher water speed in the basement shower. So part of the story for water distribution is, a huge feature of that is dealing with energy, watching it move. I told you long ago that watching energy go through a system was often a good way to understand it. This is a real case in point. Okay, so some observations about water distribution. Water is pressurized in pipes. So somebody, somewhere along the way, is pushing on the water in a way that causes it to have a pressure, to push on all the surfaces with a certain amount of force per surface area, in other words, with pressure. Higher pressure water can spray harder and higher. And this is an energy issue. Higher pressure water carries with it more energy per liter. And the more energy it has per liter, you have to talk about how much you're talking about. Having more energy doesn't tell us enough information, because are we talking about a drop of water with 1 joule of energy, or are we talking about an ocean of water with 1 joule of energy? The amount of water matters. So if it's got a lot of energy per liter, this can do things. And the two things that are interesting that it can do are it can spray harder, that is, it can have more kinetic energy per liter, and it can move higher. It can have more gravitational potential energy per liter. So a lot of the story will be the water moving its energy between 3 forms. The energy associated with pressure, the energy associated with speed, and the energy associated with height, altitude. Okay, so water is often pressurized by pumps. So just water sitting in an open pond, the water at the top surface is evidently in equilibrium. It's not accelerating, so all the forces on it must cancel, and the atmospheric pressure is pushing down on it. It pretty much develops atmospheric pressure to push back, and so the pressure at the surface of a lake is atmospheric pressure. This is sort of getting ahead of ourselves, but it's not. Just to give you an idea what the pressure is there. that's not going to be doing much good for delivering water into the third floor shower and making it do something. You have to add additional pressure to that water. So somebody's got to pressurize it. And the two classic ways to pressurize the water are pumps, which squeeze the water in a way that creates pressure and then deliver it. Or you put the water way up high in a water tower, and you use gravity to pressurize the water. Just the weight of the water way up high has to be supported by something, so it's supported by the pressure below it, and that water is supported by the pressure of water below it. You end up with a pressure gradient in the water, just like in the atmosphere. There's a pressure gradient here. We're in the middle of it. It makes balloons float. Same thing happens in water. You get a pressure gradient. The deeper you go into the water, the more pressure there is. And you can use that pressure to deliver water. Okay, so my series of questions to go through are those ones. The first of which, why does water move through level pipes? So we'll start out on the world's most horizontal town and house, one-story house, and you're just going to deliver water through that. How do you get the water to move? So first off, water, like everything else, exhibits inertia. If you get it moving, and assuming there are no friction-like effects, it'll keep doing what it's doing. So if you have you're used to seeing, you spill some water on the floor and pretty much it sits there as a puddle. But in principle, if the floor didn't have any friction-like effects, if you poured the water on the floor and gave it a little push, whoosh, it would just skittle across. I can do this. Back in a second. I don't think I've done this semester too. I can still talk to you. Ha ha ha. I told you last time or whatever that any excuse for liquid nitrogen is a good excuse. What's the purpose of this? Inertia. If there weren't friction-like effects and you got water started, it would just keep going because it's got inertia. To get it going, to speed it up and to slow it down, you need pressure imbalances to push on it. But once it's going, it's going. Water won't do this because it's got too much friction, but liquid nitrogen will. If I pour liquid nitrogen onto the floor, when I pour liquid nitrogen onto the floor, it's like pouring water onto a hot griddle. Hopefully you've seen, or skillet, you've seen water, what happens when water hits a really hot surface. It boils right there at the surface, just instantly. And the rest of the water sort of sits there levitated by that steam. The same thing will happen with liquid nitrogen. When I pour it on the floor, the little beads of liquid nitrogen are touching, from their perspective, this incredibly hot surface. It immediately boils down there at the surface and levitates the drops on that little pad of nitrogen gas. So when I pour them out here, they're going to go across the entire floor. As they do, they will pick up dirt. So they will travel along getting dirtier and dirtier, and then when they finally settle down, they will sit there and leave little dirt balls. Okay? Hopefully you can see this a bit. They're almost across the room, and they've reached the side. Can you see this? There they go. It's a race. Woo! You can see this after class too. All right? So liquids have inertia just like everything else. To get them started, though, you often need to give them a push. Here I poured them as a liquid. The act of pouring gave them some horizontal momentum, which they then carried across the room and got there. The other way in which you can get water moving, not everything I wanted to have. Yeah, it's okay. Is with pressure imbalances. Do I have anything that I can come close with? Yeah, it's okay. What I wanted was just a water straw with water in it, drinking straw with water. If you hold it horizontally, So this is, you take this as homework. Take a drinking straw, fill it with water horizontally, and then you take it up and blow at one end. You create a pressure imbalance during that moment you blow on it. High pressure where you're blowing, you're pushing out hard. Atmospheric pressure at the far end. There's a difference in pressure across that column of water. You all visualize this? That causes the water to accelerate. Like any other object, you push harder to the right than somebody pushes back to the left. There's a net rightward force. Off it goes. The alternative to water is butter. And not necessarily knowing smiles, the old roll of butter and the end of the straw. I didn't do that one, but I knew people that did. Okay, so you can make fluids accelerate towards lower pressure and therefore pick up speed and head off that direction. And so in the delivery of water to in a totally level environment, you use these two behaviors. One is inertia. Water, once you get the water started, it wants to continue going, neglecting effects that are friction-like. But in order to get it moving, you need pressure imbalances. It will accelerate from high pressure to low pressure, pick up speed, and start heading that way. Okay? How do you pressurize water? And the answer to that is you take a portion of water, and I just use this bottle to show you. So green water in here, there's a little bit of air, which makes life a little complicated here. But right now, the pressure of the water is essentially atmospheric, apart from some small details, like the pressure at the bottom of this bottle is a little greater than the pressure at the top of the bottle. How do I know that? Because the water at the bottom of the bottle has to support the weight of the water above it. So there's a pressure gradient that appears in here. So the little higher pressure down at the bottom, just like in the atmosphere. If I take the sides of this flexible bottle, which are currently basically experiencing zero net force, they are also at equilibrium. That means that the atmospheric pressure pushing in has to be balanced by pretty much atmospheric pressure pushing out. It's just like this balloon. The pressures across that balloon's skin are pretty much, there's almost no difference. Just enough to keep the balloon inflated. So the pressure inside is just a tiny bit above atmospheric pressure. The same is true here. In fact, because the skin is stiff-ish, the pressure inside and pressure outside are probably almost identical, atmospheric pressure. But if I push inward, not with atmospheric pressure, but with my thumb, then as I push inward, it has to compensate and push outward harder. The water does. So I'm pushing inward hard with my thumb. The flexible wall of the bottle allows that to happen, and that flexible wall is going, wow, that thumb is pushing hard on us. We will accelerate in the direction of that push with the thumb unless you, the water, push back. So the water develops a higher pressure to balance my inward push. Is that okay? I've pressurized the water. I have taken water that was at atmospheric pressure, and just by the act of applying pressure to parts of it, I have increased its pressure substantially. It's now it's probably twice atmospheric pressure right now. Big change. Nothing much is happening. It's all still at equilibrium. Nothing's accelerating now that I'm set up. If I open the bottle, though, you know what will happen. The water will come shooting out. Because suddenly, I will have exposed high-pressure water in the bottle to atmospheric pressure. Way below that, much less pressure outside. The water will accelerate from higher pressure to low pressure, and I'll be covered with green liquid. So next time, we'll look at the act of pumping pressurized water, pressurizing it and delivering it to something.